we are going to see today the transformer element and what are the constitutive equations of the transformer element. So we have in here we have these elements in here so that we can actually derive those equations. Now we were using the different representations in the equation form, we did it in the block diagram form, and then we did it in the bond graph form. So in here we have by the way, before I begin, you have as a picture you have a mechanical transformer and you have a hydraulic one. This is the same element that we would have if we had an electrical transformer like this, something like this, and like this, yeah, and this would be the electrical one. So let's just derive first the equations of this, and then we'll move on to doing the block diagram. Isn't it true that for this levering here, to have it in equilibrium, the lever, you would have to multiply like F1 times A is equal to F2 times B, right? But you see, this is what it's saying, the force over here times this is the force over here times this. If we write it in terms of a transformation, we could say that the force like E1 times some constant is equal to F2. So we could write it like F1 times A over B will be F2. Okay, but also you know that the velocity of one is the angular velocity times the radius. So you could say that B1 is equal to omega times A, and B sub 2 is omega times B. So if you divide both of these equations, so let's just say maybe circle this so that we know what's important here. This is one equation that's important, relates the two forces by this lever ratio. If we divide these two equations, we are going to get one that says that B sub 1 divided by B sub 2 is equal to A divided by B. Or you could say that the velocity V1 is equal to the lever ratio A over B times B sub 2. And that is going to be our second equation, see? There you go. Let's just do over here on this side. So we keep the equations going first. In here you have a hydraulic ram that on one side it has the force and the velocity. It has a piston with area 1 and another piston with area 2. So the force and velocity are going to get transformed into pressure and volume flow rate. So in here it's very obvious that if you divide the pressure, the force divided by the area is equal, you have a relationship between the pressure and the area in here. So you can write the force equals to, let's see, let me go over here and put it right in here. The force is equal to the ratio of the areas, in this case A2 over A1 times P, and the other equation is that this is the velocity times the ratio of the areas is going to result in Q. Yeah, so these are the two equations that we have for this will be the effort equations, and these are the flow equations. Right? For this one, you're going to say that you have in here the current I1, and then you have the current I sub 2 like this in here, and then we have on this side we know you have voltage 1 and voltage 2, and this, let's say, the transformer modulus M. You have a situation here where you have that voltage 1 times the M would be equal to voltage 2, but because it's power conserving, I1 is gonna be M times I sub 2. This of course not velocity but voltage. Yeah. See, and these are the equations for that we have for the transformer element in electrical domain. So how do we actually build a block diagram of this? What you have in this case is that you have a signal in here. This is going to be F1, and then gets multiplied by this lever ratio, like this would be A over B, and out comes F sub 2. But this has to have a companion equation, and that is an equation that has the other variable transformed. That is, in this case, B sub, this goes like this. Yeah, F1 times this is F2. This is like this. And so this is B sub 2. And this is B sub 1. That A over B, the lever ratio. So this is the block diagram for the one in the mechanical domain. We can have a block diagram for the other one. In this case, this one is drawn a little different. That's good because it illustrates that in here we have this P gets multiplied by B, A over 2 over A1, and out comes F. So A2 over A1. And then over here we have the opposite. This would be A2 over A1 like this, where you have the B sub 1 this, it produces b sub 2. On this particular one in here, I sort of feel uncomfortable with it drawing in the way it is, so I'm just gonna make it a little nicer, okay? So let's just do that, and we have maybe like this, and this is going to be a sub 2 over a1. There you go. I like this better. In this one, these equations are telling us the following, that if you have the voltage here V1 and it gets multiplied by this M, you're going to have B sub 2, and also that on this side you have I1 is equal to the the ratio in here like this. This is I2. So I2 times M is I1, and B1 times M is B2. Okay, so this is how we represent it in the block diagram form. The bond graph form is much more compact, and in this case you have that the input in this is on this side F1 and B sub 1, and you have a TF element like this, where this is F sub 2 and B sub 2 and B sub 2 like that. And then we need to put the causal marks in here that will give, see the way the equations are written, it says that B1, no, it says that F1 times the modulus is F2, so this, it would be, the modulus is A over B, so you have F1, this, the effort, so it's gonna be like this. And this is this form. Now you could have this other form, and in doing this I'm saying that it really doesn't matter which form you have it. Most important thing is that it coincides with your model. So this is P1. Sorry, here's a correction. This is Q. I didn't know. Just wondering here. This Q here, and then you have on this side you have F and B sub 1. So if we have the causal marks for these equations, it reads this. No, it reads this way, and this other one reads the other way. So in this case you have like this, and then this. Yeah. This in here you have, wait a second, I think we have a problem in here. The equation here has, yeah, see, I knew there was something in there. Glad I realized it now. It's gotta be the other way, because of the way the equation is written. Let me have you reflect. It says that this times this is the first, so this one has to be like this, see? And there on this side you're going to have that this is like this, and you have a TF, and on this side you're going to have the voltage and the current, this voltage 1 and current 1, and this is the modules M in here, and in this case you're gonna have this B1 times M is equal to B sub 2. That's this one in the bond graph form. So you can have all these two kind of causalities, but what you cannot have is something like this. You will never have this, because it's contrary to what the element is supposed to do. Here you have a flow in here, and you have an F or up. So, or you could have something like this, also would never work. While on a generator they work. But I want to, let's just stop here for the explanation of the TF element.